All right, everyone. Welcome to our third installment of our calc review. Today we'll be going over another set of derivative rules, and we'll also be getting into partial derivatives and doing some examples. So, like I said, I'll cover these in this slide, and I didn't change the meme, so sorry. And we've already done these four rules plus the constant rule. We're also, so in this set of slides, we're going to work on the chain rule, an exponential rule, and a logarithm rule. And then, like I mentioned before, it's not exhaustive, but this is going to cover the most likely rules that you'll need for this class. So first, the chain rule. All right, so if a function can be written f of x equals g of h of x, then the derivative of that is um, the derivative with respect to h of x. It's this kind of ugly notation. All right, so this rule is used often, and it's used with the other rules as well. It's really important that you know it, even though the notation is a little bit opaque. It's not really invincible, and it can be roughly interpreted as you take the derivative of the outside and then you just multiply by the derivative of the inside. I'm not really a huge fan of the book's example because it didn't make it that much more clear for me. So I'm just going to give you one example now, and then as we do the other rules, give you an example as we go. And I'm hoping those will cover the main use cases for this class, but again, it's by no means exhaustive. So we got, oh man, is this exhibit? I don't remember. He's the guy from Pimp My Ride. He says, "Yo, dog, I heard you like calculus, so I put an X in your X so you can derive while you derive instead of drive." Get it? Anyway, I love that meme. So, um, we're gonna find the derivative of y equals 3x plus 4x squared to the 4. And so the first thing that we're going to need to do is notice that this is the whole thing to the fourth power is our g of x, our outside function. And then the inside, the 3x plus 4x squared, is our h of x. And so we first need to take the derivative of the outside by using the power rule that we were using in the last set of slides. So this is y prime equals 4 times 3x plus 4x squared to the 3. Notice that we just brought the 4 down out here and then subtracted 1 from the exponent, okay? And so if you forget to use the chain rule, then you'll just leave it like this and it'll be wrong. Like Lil Pump said here, he said the d of x, d dx of f of g of x is f prime of g of x. Well, g prime of x is like, am I a joke to you? And so what we do is we need to take the derivative of the inside, the 3x plus 4x squared also. And then multiply it. And so this is needing to multiply by the derivative of the inside. This is the chain part. And so we know that that is just 3 plus 8x after we do the power rule to both terms, because we can do the power rule to both terms via the addition rule. So see, we use the power rule, the chain rule, and the addition rule all in the same question. And so we get the derivative is 4 times 3x plus 4x squared to the third power times 3 plus 8x. And so we could kind of foil this, not foil this, but we could multiply 4 by 3 times 8x if we wanted to, but we're just going to leave it at this. This is an acceptable answer for the derivative of y. And again, I'm going to point out that this is what we mean by the chain part. It's the derivative of the inside of this power. So that's the chain rule, more or less. All right, so the next thing we have is the exponent rule. So if there's a differentiable function g of x, then the derivative of e, which is just a number, to the g of x is e to the g of x times g prime of x. And so, this is the chain rule right here. And so example one will make this memes more interpretable for you. So if we have y to the e of x, and we do y prime times is e of x again times x prime, so that's the derivative of the exponent And then we see that this is just e to the x times 1 equals e to the x. And so that's where the meme comes in. We have e to the x, and we breathe the derivative on it, and it just comes out looking like e to the x still, no matter what. And so that's where the meme comes from. Let's do a slightly more difficult example. So if we have y equals 2 times e to the 3x squared, then the derivative is 2 times e to the 3x squared times the derivative of 3x squared. And so we leave this 2 times e to the 3x squared, and we take the derivative of 3x squared, and we get 6x via the power rule. And then we can simplify that, and that's just 12x times 3 to the x squared. And so this times 3 to the x squared is where the chain rule is happening. And so while I'm on my Game of Thrones memes, brace yourselves, because here come derivatives with logarithmic functions. So the logarithm rule is pretty easy too. If the function is y to the log x, then the derivative is just uh, 1 over x. And we need to do the derivative of the inside of the log, so x prime. But we know that x prime, the derivative of x prime is just 1 via the power rule again. And so the derivative is 1 over x, which we know is also x to the negative first power. All right. And this times the x is from the chain rule. So you've seen 3 examples now of where the chain rule needs to be applied. All right. And then our example I'm going to run through is 5 times ln of x squared. So we have y prime equals 5. Remember, 5 is just a constant, times 1 over x squared times x squared prime. So we need, this is the chain rule, the derivative of x squared. And the derivative of x squared is just this 2x times 1 over x squared. And so after simplifying it, we can get it down to the derivative just being 10 over x. Logarithm rule, pretty easy. Probably won't see it too much, so I'm not going to belabor the point. And again, this is where the chain rule comes in. All right. Partial derivatives. These you'll have to do a lot of. And so if you can calculate a derivative, you can calculate a partial derivative. That's what I say to people who are like, but I've just had Calc 1. I don't know what Calc 3 is, so I don't know how to calculate partial derivatives. Well, guess what? I know you can do it. And if you don't know this movie, shame on you. All right, partial derivatives. These are taught in Calc 3, multivariable calculus. So it's even Calc 1's not a prereq, so you probably haven't had Calc 3, but you might have. You should know that partial derivatives are very manageable, and you will also see them in upper level data analysis econometrics, which I recommend for all econ majors or minors, and was actually required at my undergrad. So anyway, let's say we have some function, utility equals f of q1 and q2. So how happy you are depends on the consumption of good 1 and good 2. The partial derivative with respect to q1 is just this du dq1. Those should actually be curly d's, like these down here. And the book is, you should know that the book is just going to simplify this notation to u under subscript 1. And this derivative, you need to think about what it means. It means, how does utility change with small changes in just good 1? So it's the marginal utility of good 1. And so the straightforward next question that you have for me is, what do I do with Q2? In Calc 1, I didn't have to worry about Q2 at all. Well, remember what du dq1 is. It's telling us how much utility changes for a change in good 1. Ceteris paribus, all else constant. So what we do is we treat Q2 as a constant, and we can use just like constant rules. We just think of it as some number, not a variable. So if in a partial derivative of du dq1, q2 is just some number. It's not a variable. It could be 5, 10, 20. That's how you should think of it. All right, and so I want to give you a motivating example of partial derivatives from economics. So something economists are interested in is how your skill set affects your outcomes. And so a way we divide skills is into cognitive, like IQ, and into non-cognitive or socio-emotional, like EQ. That would be your soft skills, like communication and leadership and those kinds of things. And so we're interested in both how cognitive and non-cognitive skills contribute to, say, high school completion, and other outcomes in general. And so we know that, or I probably don't have to make you believe that your other skills besides just your IQ, things like your motivation and your communication and your leadership, are also probably important in how likely you are to complete high school. And so I'm going to show you this, which will hopefully, well, not hopefully intimidate, but might intimidate you, but it will also give you some idea of what's happening. So this graph is going to show you how high school completion depends on both cognitive and non-cognitive skills. So this is your probability of completing high school, and you notice that it ranges from 0 to 1 like a probability would. And so the highest point we see is this like 0.5 over here. And these are for the people who have the lowest cognitive and lowest non-cognitive ability are the most likely to drop out of high school. So it shouldn't be too opaque or non-intuitive. If you have low cognitive and low non-cognitive skills, you're the most likely to drop out. And so instead of that neat line that you're used to seeing, now we have a three-dimensional plane because we have a function of three variables. We have how likely you are to drop out depending on both cognitive and non-cognitive skills, just like we had utility maybe depending on the consumption of good one and good two. And this is from this Heckman et al. Article. You can click on these links. This one is behind a paywall, but you can find it if you Scholar it or WVU Library it. And then this goes to a working paper that has lots of different outcomes, one of which I'll show you later. But if you're interested in other things, then you should click here and go check out. Anyway, so on in this plane, we were interested in like this. We have dropout being a function of two variables, cognitive and non-cognitive skill. Let's say we want to know the partial derivative of dropout with respect to cognitive skills. That is, so for somebody who has the same non-cognitive skills, but we just change their cognitive skills a little bit, how does that affect their probability of dropping out? So that would just be this axis is the cognitive skills. So d dropout, d cognitive is holding non-cognitive constant and saying, okay, as we increase or decrease our non-cognitive skills in kind of the same row, how does that affect our probability of dropping out? And so you can see kind of this, it's really steep here, and you can see that really steepness here in this graph here that shows you what's happening on this plane for just one variable. And so what it kind of does is it holds non-cognitive ability constant, and it just moves along this axis here. And so you can see that we can characterize that partial derivative and show how, like, if we alter our uh, cognitive skills a little bit, that is, like, we go from not that skilled to very skilled cognitively, how is that going to affect our probability of dropping out? And for somebody with the same amount of non-cognitive skills but the least non-cognitive skills compared to the most non-cognitive skills, they're less likely to drop out. And so here's just one more example. This is a probability of employment at age 30 for females, and we can see that it doesn't matter very much for females if they become more cognitively gifted, how it affects their employment at age 30. See, it's kind of pretty flat as you go along the cognitive axis, and you can see that in this graph. But what kind of stands out to me is as females become more non-cognitively talented, there's this kind of really steep slope here that then levels out. So as they become more non-cognitively um, gifted for the same level of cognitive ability, they become much more likely to be employed at age 30. And so this is kind of just like another interesting use case I find from this. And so let's take this intuition and motivation into when we actually take partial derivatives of equations. So are you ready to compute some partial derivatives? So our function is y equals 5x1 squared plus 3x2 squared. And we want to find partial y, partial x1, the partial derivative of y with respect to x1. By the addition rule, we know that this is just the derivative with respect to x1 of this plus the derivative of x1 with respect to this. The left term is pretty easy. It's just 2 times 5, and then 2 minus 1, and we get 10x to the first on the left side, plus whatever the derivative of this is. And so remember when I said the right side, that x2 is a constant because we're not differentiating by x2. So it means that x2 is just a number in this example. So 3 times some number squared is just a number, which is just taking the derivative of a constant is just 0, like we saw in the derivative rules 1 slides. And so then we know that dy dx1 is just 10x to 10x1. Easy. All right. I look like I have some animations here. So anyway, what constant means and the implications for partial derivatives. All right, it's important that you don't equate constant with it meaning just it becomes 0 and I can ignore all the things that I'm not differentiating by. That's wrong. We have constants that don't drop out of the derivatives. For example, if we have y equals 4x squared, y prime is 2 times 4 times x. So the 4 didn't just go away magically in the derivative. And I'm going to show you examples of where it matters for partial derivatives of two variables as well. So here's an equation where utility depends on good 1 and good 2, and z, a, and b are all constants. They're just some number. So we need to find the derivative of u with respect to q1. And so by the derivative rule, we know that this is just the derivative of the left term plus the derivative of the middle term plus the derivative of the right term. And so the derivative of the left term is 1. Like, so that would just like, it's x or something to the first power, and you multiply that by 1 and then subtract the power off. So by the power rule, this is 1. And then by the constant rule, because q2 is just a constant, q2 is 0. And so now we have the left and the right terms, and now we just need to worry about the middle term, which I'm going to walk us through. First, I want to rearrange it algebraically to where u times q2 to the b times q1 to the a. And remember, we're differentiating by q1. So what's that mean for z times q2 to the b? It means that z is a constant, q2 to the b is a constant, and then we need to take the derivative of this. And so we know that this z times q2 to the b power is just some number. And we can just treat it as such. We can just treat it as a constant. We don't need to do the power rule or anything like that. I mean, we don't need to do the product rule, excuse me. And then we can just do the power rule on q1 to the a, and we'll have this 1 plus z times q2 to the b times a times q1 to the a minus q1 a minus 1 plus 0, which just simplifies to this. And this is a perfectly acceptable answer. And notice that just because we differentiated by q1 doesn't mean that q2 just went away. It means we treated it as a constant, not just something that we could just forget about. All right, so a popular way to specify in economics is a Cobb-Douglas. It's used for utility and production pretty often. And so Cobb-Douglas utility is u equals q1 to the a times q2 to the 1 minus a, where a is between 0 and 1. The reason it's so popular is because it satisfies the assumptions of diminishing marginal utility or diminishing marginal product if it's used in a production function. And these are true due to the restrictions I put on a here. So a and 1 minus a has special interpretations in many economic applications, but I want to show you one example of taking a partial derivative when the function is Cobb-Douglas. So let's say we have Cobb-Douglas utility where your utility depends on q1 and q2, and we want to find the derivative of utility with respect to q1. All right, so by the product rule, we know that this is the derivative of q1 of this times q2 plus q1 times the derivative of q2 to the 0.67. All right, so let's again break this down into a familiar left term, right term, and let's do the right term first. So in the right term, we're taking the derivative of a constant because we're not differentiating by q2. So we know that q2 is 0, and then q1 times q1.33 times 0 is just going to be 0. And so we know that the right term is just become 0. All right, and now that we need to do the left term. All right, when we do the left term, we can use the power rule on it and get 0.33 times q1 to the 0.33 minus 1, and then just times q2, which is a constant, to the 0.67. And then with a little simplification, by algebra, it gets us to du dq1 equals 0.33 times q2 to the 0.67 times q1 over 0.67, or to the 0.67. Because yeah, this is a negative exponent, and so we can move it to the denominator and make it no longer a negative exponent. And so that's it. That's Cobb-Douglas utility. And the rest of the derivative rules, again, I put these extra resources here for you because I am not a calculus teacher, and I don't directly apply calculus many times as much as these other people. And so I suggest you take a look in these other places or ask me if you have questions that you think I can help you with. Thanks for sticking with me through derivative rules 2, and I'll get back to you with how we use these derivative rules to find extreme points of functions, which for economics means that those extreme points represent optimum decision making for individuals, which is pretty cool. So thanks for sticking with me, and I'll see you in the next set of slides.